Hello, we're going to be continuing with the second part of our interparticle forces. In this lecture, we're just going to be solving problems on interparticle forces alone. That's what we're going to be doing. We're going to be focusing on only solving problems because the first one, we talked about the concepts and introduced important theories regarding different types of interparticle forces. And now we're going to be solving problems on them immediately. But before we do that, I have a beautiful quote by one of the greatest scientists that ever lived and worked on this earth, Albert Einstein. He said, insanity simply means doing the same thing over and over again and expecting a different result. That is Albert Einstein. So at times, if you want to make a change, if you want to get an improvement, there should be a change. And that is just the message from Albert Einstein of the blessed memory. Let's just get into it. Of course, we're still going to be addressing two of those objectives that were addressed in the first part of this lecture. We're going to now begin to apply the understanding of these intermolecular forces like we did, and then we're going to use it now to again make informed predictions on the physical properties of substances, and those physical properties will be boiling point, melting point, solubility, vapor pressure, surface tension, and capillary action. Let us get on with it. Problem 1. It says, arrange the following in order of increasing interparticle force. So we've been asked to arrange it in order of IPF. Of course, remember when we looked at the interparticle forces, we looked at different types of interparticle force. So what we're going to do first, usually in this kind of problem, is to first of all look at the molecules or the chemicals or the compounds you're given and begin to understand what nature are they. Are they polar substances? Are they non-polar substances? Are they ionic? And now begin to make those informed decisions. Now, if you look at these guys, now going from your periodic table, all these guys, all these atoms belong to group what? They belong to the group 8 elements. We have the argon, we have neon, we have xenon, we have helium, and we have krypton. All of them are of the noble gas. And if you look at all of them, they are all non-polar. Of course, these guys do not, all single atoms or atoms of similar or diatomic or triatomic, or if you say triatomic homatomic molecules or diatomic homatomic molecules are all non-polar themselves because they are very symmetric. Just remember that. So what does that simply mean for us? What it means for us is that all these molecules are all non-polar. That's the first thing, because they're single atoms. So if they're all non-polar, one thing will decide. One factor will decide on what is going to happen to them. And what would that be? The factor that would decide in arranging them in the strength of the intermolecular forces is going to be what type of bonding London dispersion force. And what are the factors that affect the non-dispersion force? We said the size of the atom, or the number of electrons, or the molecular weight, or you can say the relative atomic mass, since these are all atoms. So if you look at all these atoms now, we find that we're going to look at which one has more electrons. So all these molecules are non-polar, and so they will have only London dispersion forces. So let me begin to write my reasons. It says, explain your reasons. So before I do that, I want to arrange them first of all. If I arrange them, I'm going to write my reasons to the right. So first of all, helium contains only 2 electrons. It's going to be the smallest. I'm going to start from there. Helium, because I know that the number of electrons, the higher the number of electrons, the higher the intermolecular force. So what it simply means is that the lower the number of electrons, the lower the intermolecular force, or the lower the London dispersion force, because that is what we're looking at here. Now neon, helium is followed by neon. Neon has only 10 electrons. And neon will be followed by argon. Argon has 18 electrons. And this will be followed by which one? Now, after argon is 18. So krypton is, what I have here now is krypton is 36. And xenon is 54. So what that simply means is that I'm going to put my krypton next and then followed by my xenon. So this will be in increasing order of interparticle force. So what are my reasons? Now I'm going to state my reasons here. So now all these atoms, of course, all these atoms are non-polar. They're all non-polar molecules, and only have the London dispersion force. Remember, it's called LDF. So my arrangement will be based on size. So the size, if I don't want to say this, I can say this, the size, or I can say the number of electrons, or you can say the molecular weight, whichever one, or you can say the molecular weight. Is what decides this arrangement. Determines the strength. So the strength will be determined by the intermolecular force. So that's exactly what it means. So xenon has 54 electrons and will have the strongest IPF, while helium has only 2 electrons and will be the least as shown. So this will be the reason. On the other hand, let's look at the second molecule. Now, if you look at all this, that remember what I said earlier when I started this lecture, I said all homoatomic diatomic molecules are usually nonpolar. Most homoatomic diatomic molecules are usually nonpolar, because what it simply means is that they are very symmetrical. They're very symmetrical in nature, and because they are symmetrical, if you draw the Lewis structure, you find out that they just have 2 atoms that are on both sides, and then these molecules are all non. So again, these molecules are symmetrical. Because they're all symmetrical, they are all nonpolar. All nonpolar. These are all nonpolar molecules. All nonpolar. Now again, if they are all nonpolar molecules, what is going to decide? We're going to use their molecular mass to decide what will be the strength of the interparticle or intermolecular force in them. So now what it simply means, let's look at, if you look at this now, if you look at your periodic table, now nitrogen is smaller than oxygen, oxygen is smaller than chlorine, chlorine is smaller than bromine, and bromine is actually smaller than iodine. So it's already arranged. I don't know, that's a coincidence. So N2 will be less than O2 in strength. This will be less than Cl2. Cl2 will be less than Br2, and Br2 will be less than I2. Now, so again, remember, LDF increases with increase in atomic mass. So always remember that the London dispersion force increases with increase in atomic mass or molar mass. We can let's say molar mass. Again, what this simply means is that in this molecule iodine, I2 has the greatest molar mass, the largest mass. If you calculate the mass, just multiply an atom of iodine times 2, and that's actually going to give you 253.8 grams per mole of it. While N2 has the lowest mass, and the lowest mass is what? Is just 28.02 grams per mole. So what that simply means is that N2 will have the least IPF, and iodine will have the most. And the reason is because it has the lowest, and this is actually the arrangement in increasing order of strength of the intermolecular force. Good. So this is exactly the reasons. So anytime you have non-polar molecules that of course do not have that are not polar, that are non-polar, they don't have the dipole-dipole or hydrogen bonding, the size of the atom or the number of electrons takes precedence. Let's go to the second problem. It says, arrange the following molecule increasing boiling point and give the reason for your answer. Now, if you look at all these molecules, let's look at them a little bit. All these molecules will have polar molecule because if you look at each of them, they are all diatomic, heteroatomic molecules. What it means is that they contain two different atoms and they have only two atoms in them. Now, if you look at this now, we're going to consider the effect of what? Electronegativity. Electronegativity will play important role. Electronegativity. Now it's going to play a role. If you look at all this, the electronegativity of all these three, find out that, remember earlier what I told you, fluorine is the most electronegative element. And electronegativity increases as you go from what? Left to right of the periodic table. If you go from left to right, En increases. As you go down the group, En decreases. That's actually how this happens. And what's interesting about that? The interesting about En is that if you look at all this one, hydrogen fluoride has the strongest electronegativity. Fluorine has the strongest electronegativity. So the difference between hydrogen and fluorine in the electronegativity will be higher. And that will make this to be actually the strongest bond. And not just that. Remember, hydrogen bonding is that type of bonding that occurs when hydrogen bonds with the most electronegative elements. And one of those is what? Fluorine. So whenever you have hydrogen and fluorine, this molecule is going to make a hydrogen bond. Now, hydrogen bond is stronger than every other ones here because the other ones here are going to make what? Dipole-dipole force. So if you draw, these ones are all polar, but they're going to make dipole-dipole. So assuming I want to draw this, let me draw it a little bit. If I want to draw each of these, so HF, of course, this is partial negative, partial positive. This is HI, partial negative, partial positive. This is HCl, partial negative and partial positive. And this is this is HBr. That's what I want to say. HBr. This is partial negative and partial positive. If you look at all of them, they're all dipoles. All these molecules form dipole-dipole interaction. All these molecules have dipole-dipole interaction. However, what are we going to use? We're going to use electronegativity. So the electronegativity value En will be a deciding factor. Yeah, it's going to be a deciding factor. So what is it going to be? Let's see. Since this is the most electronegative, so it's going to be the strongest. Followed by, this is, if you go down the group, this is further down the group. So we're going to start from that one. Since it's further down the group, no, the further down the group is iodine. Sorry, bromine comes before iodine. So we're going to start with, so Hi actually will be less than, followed by bromine is further down the group, and this will actually be less than. Chlorine is actually in row 3, and this will be less than HF, which is in row 2. And HF has the strongest here. So what is the reason? Now, since HF has the highest electronegativity, it forms hydrogen bonding, which is stronger than the dipole formed in the rest from HBr to HCl and HI are all dipole interaction. So of course, I told you earlier, in order of strength, hydrogen bonding is actually stronger than the dipole-dipole interaction. And on that note, as a result, HF, we have the highest boiling point because more energy will be used to break the bond. The bond, of course, is hydrogen bond. Don't forget that. Now let's go to problem 3. In problem 3, it says use dotted lines to illustrate how this molecule will interact with itself, and we should name that. Now, if you look at this, remember, this is a hydrogen bonding. Hydrogen bonding occurs between NOF. NOF is nitrogen, oxygen, and fluorine. So we have nitrogen here, and we have hydrogen connected to it. So this is going to be what? So the type of bonding here, let's name it first before we draw, will be hydrogen bonding. So we're going to draw how ammonia, this is actually ammonia, will interact with itself. So what are we going to do? I'm going to leave this one I draw here. I'm going to start with a fresh one. So if I put this one here, you don't have to show me the thick lines. Just know that this is partial negative, partial positive, partial positive, partial positive. So this is going to connect with another molecule here, N, that is partial negative. This one is going to connect with another one here, M. This one here is going to connect with another one, N. This one, and then you can also connect another one from here. It doesn't matter. You can decide to connect another one from here. So this is how this particular molecule interacts with itself. And these bonding are what we call the hydrogen bond. This is a hydrogen bond. Again, remember that we represent the intermolecular forces with just the dotted line. And like I said earlier, this type of bonding is called the hydrogen bonding. Let's go to the next problem. The next problem is it says, list all the types of intermolecular force that can occur in each of these molecules. What are those types of intermolecular force that can occur in each of these molecules? So what are we going to study and inspect these molecules individually and understand them? Let's start from this one. This is ammonia, just like I have here already. So that is an easy way for you to figure that out. So when you see a nitrogen attached to a hydrogen, the first thing that begins to come to your mind that this must have a hydrogen bond, Hb. Again, remember, hydrogen bond is a type of dipole-dipole interaction. So any molecule that has a hydrogen bond must have a dipole-dipole interaction. And again, lastly, all molecules must have London dispersion force. No matter whether they are polar, non-polar, or ionic, they must have a London dispersion force. Now again, let's look at this one. Now, if you look at this molecule looks highly very symmetrical. And not just that, I told you earlier, anytime you see carbon connected to a hydrogen bond, it is a non-polar bond because the electronegativity of these two molecules is very close. Hydrogen is 2.1 and carbon is 2.5. If you look at the difference, it gives you about, the difference in En gives you about 0.4, which is in a direction of non-polar. So this is actually a non-polar molecule. And non-polar molecule only have only one type of intermolecular force, which is what? London dispersion force. And that is it alone. And now going to the last one. The last one here now, also we're going to apply. Now remember, every molecule must have the London dispersion force. So let's start from there. Having not established that, now if you look at the difference in electronic between silicon and hydrogen again, the difference in electronegativity is very close. It's very close, just like as we have in carbon and hydrogen here. So this bond is actually non-polar. However, if you see the electronegativity difference between silicon and oxygen, the difference is actually high. So this actually becomes a polar bond. So this will actually be a partial negative bond. This is a partial positive, making this a polar bond. Remember this partial positive, no, partial negative, partial positive, partial positive, and partial positive. So what that simply means is that if this bond is polar, makes this thing to be a polar molecule. And every polar molecule will always have what type of bonding? A dipole-dipole interaction. So these are the types of intermolecular forces that can occur in each of these molecules. We've just listed those. Feel free to always pause this video, try to practice with yourself, and particularly with the introduction of this concept in the first part of this lecture. Look at it, try to solve some problems yourself, and always get back to the video and check them for comprehension and correctness. Again, it says name the type of IMF that exists in the molecules below and show how each of them will interact with each similar molecule. So we're going to name it and we're going to show how it interacts. Again, let's look at this. This is like the first one I had earlier. Now, if you look at this bond, carbon to hydrogen, the difference is high. This is about 3.5. This is 2.5. This is about 1. So what it means is that this bond is a polar bond. If this bond is a polar bond, that means for this thing to exist in itself, it must have to interact with itself. It has to do that with what? A dipole interaction. And since it uses the dipole interaction, how will it interact with itself? Let me draw it. So I'm going to draw this way. This will interact with itself here. And I'm going to try to draw. This will have to interact with the oxygen in the other one. So I'm going to make it this way. And then this will interact with this. So this is partial negative, partial positive. This is partial positive and partial negative. And this is what we call a dipole-dipole interaction. The same thing happens here. Now, hydrogen here is 2.1. Chlorine is about 3.0 or thereabout. The difference in electron will make this thing is at least much. And because of that, this will be a partial negative to a partial positive. So again, this is a dipole interaction. Can occur in this molecule. And if I'm going to show that, what am I going to do? I'm just going to draw the first one. This will have to interact with another one this way. And this will have to interact with another one. So this is partial positive, partial negative, partial negative, partial positive. And this can also interact with another one here. There's a partial positive. And this can also interact with another one here. This is partial negative. So this is also an illustration of the dipole-dipole interaction in all these molecules. So this is D. This is also the dipole-dipole interaction. Dipole-dipole interaction. All right, let's go to the next problem quickly. Problem C says, arrange the following molecule in increasing order of melting point and vapor pressure and give your reason. And I provided the place you need to arrange them yourself. Now let's begin to look. The first thing we need to inspect, what type of molecule is this? Is it polar or non-polar molecule? Now a quick look at this. Remember again, I've said it. It's always good to remember. Anytime you see a carbon to hydrogen bond, you can memorize it to know that this is what? Non-polar bond. And if you look at this molecule, what we see is carbon to hydrogen bond. What it simply means is that this molecule, all these molecules are non-polar. And when molecules are non-polar, what decides? London dispersion force. What decides the strength of the London dispersion forces is going to be what? So all these molecules have London dispersion force. And what would I mean? The strength of London dispersion force 1 is the size of the molecule, surface area, and the number of what? Electrons. We're going to see which one is playing out here. So if you look a quick look at these three, let's count the number of carbon atoms. That will tell us how long they are. This is what? Let's count. This is 1, 2, 3, 4, 5, 6. 6 carbon. This is 1, 2, 3, 4, 5, 6 carbon. This is 1, 2, 3, 4, 5, 6, 7. This is 7. If this is 7 and this is 2, then what it means, if you have a machete, it's going to take you longer time to cut this guy than to cut the other two. So what does that simply mean? What it simply means that this is going to be the one with the what? Highest melting point. So we're going to put it. We'll go to the melting point. This will be the, and this I arranged it from lowest to higher. So the highest melting point is going to be C. And that's going to be followed. Now, between these two, we cannot use the molecular weight because the molecular weight or the size, they have the same thing, 6, 6. What is going to come into place? Let's look at the surface area. If you look at this, this is longer and occupies more space, but this is condensed. If you look at this molecule is condensed more than this. So this is more open. This is more open. Let me say more open. Because this molecule is more open, it will have more surface area. So it means more surface area than this one. So that means this is going to follow. A is going to follow. A is going to be in the middle, and then the lowest is now going to be the B. So B is going to have the lowest melting point followed by A and followed by C. Now remember, the best thing I tell students is to know that the strength of the melting point or intermolecular force characteristic is the opposite of the vapor pressure. So we can see that. Now, okay, let's go back to what we have here. Remember, for vapor pressure, the stronger the strength of the intermolecular force, the lower the vapor pressure. If this molecule C is the longest and has the strongest London dispersion force, what it means is that it will have the lowest vapor pressure. So if it's going to have the lowest vapor pressure, what it means is that it's going to be C, followed by which one is in the middle. The one in the middle is A, and then what it means is that B is going to be what? The highest vapor pressure. So what is our reason? The reason on the first one is that C, for vapor pressure, C has the what? C has the highest molar mass. Because it has 7 carbon atoms. Remember that. You have 7 carbon atoms. So if you calculate the molar mass, or you can say longer chain. That one is obvious. Longer chain. It has a longer chain. Then followed by A. Now A and B has 6 carbons, of course. Remember that? Both of them has carbons. However, A has a larger surface area because it's more open. It has a higher surface area, and that's why. And B is more condensed. B is more condensed. Yeah. So it has least surface area. Least surface area. That is the reason. Yeah. So I know, and for vapor pressure, George just said that the vapor pressure is opposite. Just use that way because I don't have more space here. It's the opposite of the melting point. So it is the direct opposite of the trend of the melting point, because molecules that have the weakest strength, the weakest intermolecular force strength, will have the highest vapor pressure. All right, let's go to the next problem. It says arrange the following molecule in increasing order of boiling point, vapor pressure. Again, that's what we're saying here. It's a boiling point. Oh, okay. I think I missed something here. I have boiling point and surface tension. Okay, please, you're going to help me to correct this. What I have here is boiling point. I'm supposed to have boiling point, surface tension, and solubility. So this is supposed to be the surface tension. Let me say surface tension, please. Surface tension. Now, but I have it correctly here. Now, let's look at this molecule. Now, if you look at all this molecule, all of them have a ring, something that looks like a pentagonal ring in each of them. The difference lies in this attachment at this point. Let's look at them. First of all, when you look at this, these only have carbon and hydrogen. So this molecule, of course, will be non-polar. Let me label it. This is a non-polar molecule. And of course, all of them have similar masses. For you to make this kind of comparison of polarity of molecule, you need to have molecules with similar with similar masses for you to make a coherent judgment without having to use the effect of the dispersion force. So let's see what is going on here. Now, if you look at these two, if you look at these two now, you find out that the difference between these two, this is OH and this is NH2. OH molecules means that both of these molecules can hydrogen bond. So this molecule can hydrogen bond, this molecule can hydrogen bond. However, between these two hydrogen bonds, OH and NH, which one is stronger? Remember on the first part, I told you that it depends on which one has the higher electronegativity. Between oxygen and nitrogen, oxygen has electronegativity of what? 3.5. And nitrogen has electronegativity of about 3.0. So what it simply means is that the hydrogen bond will be stronger in this molecule than in this one. So to arrange, it said arrange it in what? In increasing. So I already put it here from lowest to highest. So the lowest here will be the one that is non-polar and will be the lowest in boiling point. And which one is that? The non-polar is going to be this one. For the non-polar molecule, we're going to have what? A will be, because it's a pure non-polar molecule, there's a non-polar molecule just have only London dispersion. Remember, this will be London dispersion force is lower than the other two. This will be followed by these two. Between these two, which one has higher electronegativity? This one has higher diamonds. The middle one is going to be C, and then B is going to be the strongest. Now remember, the strength of the intermolecular force increases with increase in both the boiling point and the surface tension. So for this one, it's going to be exactly the same pattern. The surface tension increases as the strength of the molecular force increases. And the same thing goes for what? The solubility. I just purposely put this term here. So both the solubility, the surface tension, and the boiling point has the same trend. The stronger the intermolecular force, the higher the boiling point, the surface tension, and the solubility of that compound. So what is our reason? The reason we have to do this is that the OH bond, the OH group or bond, you can say the OH bond is in B. Of course, is in B. I know. I don't have to say it. Yeah, the OH bond in B. Let me just write it. In B is stronger than NH bond in C, because oxygen has higher electronegativity, higher En difference. Or I would say because OH bond, okay, let me put it that way. Let me just make it completely. Because OH bond has higher change in En difference due to higher En value of oxygen compared to that of which one? We compare with that of NH. So it is actually better. Then lastly, A is non-polar and only has the London dispersion force. So it will of course have the lowest of all the properties of all. So this is the arrangement and these are the reasons. We go to the next problem. The next problem says using only diagrams, illustrate how water will interact or dissolve or hydrate the following molecules. Now if you look at this molecule, potassium, this is an ionic compound, ionic. Of course, this is because of this OH, this is what? A polar compound. So what is going to make an ion dipole interaction here is going to make dipole. So let's start with the first one. If I start with this, now KF dissolves in water. If this is solid, if it dissolves in water, It's going to hydrate and become K plus aqueous plus F minus aqueous. Now, how will water interact with this? Water will hydrate these guys individually. Let's write that. So for potassium here, I'm going to give more space for myself. So for potassium here, ion, it will be surrounded by the negative side of water. Don't forget to this is ion dipole interaction, or you can say dipole ion interaction. It doesn't matter the way you want to put it. So there will be an interaction here, and then you can decide to put your polarity. But this is partial positive, or hydrogen is partial positive, and this is partial negative, and partial negative. And then what about that of fluoride? For the fluoride, again, the fluoride will be surrounded, let's put it here, fluoride will be surrounded by the hydrogen molecules. It will be surrounded by the hydrogen molecules. So this is what we're going to get here. And then I'm going to put those bonds. So it's going to be this will go here. Good. And then we cannot put, so every oxygen is partial negative. Remember that. Don't forget every oxygen. Partial, you have to put the delta notation. This is partial positive, 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 partial positive. So this is how water will hydrate potassium fluoride. What about this one? Since this is a polar molecule, remember this interaction is actually called what? Ion dipole interaction. This is what we have here. Now, what about this one? We have a space here. I think it can go. This one will form dipole interaction. What would that be? Okay, let me draw that one. So if I get back my red, I'm going to see that this C here. Now remember, carbon to hydrogen bond is non-polar. We don't have any interest. But for this one, there's an interest. So what are we going to do? Now water molecule is going to begin to surround this one. Now here we'll get to this O can interact with this O here can interact with a hydrogen at this point, and this one can interact with an oxygen, and then which other thing here? There's an interaction here. And then remember, now these two, this is a polar bond too, because this is partial positive, this is partial negative, this is partial positive. This one can also interact with another molecule of water from the oxygen side. So this, all we have here is what? Is dipole-dipole interaction. So what I can form both hydrogen bond from this side, this is a hydrogen bond, this is a hydrogen bond, but from here is a dipole-dipole interaction. And if I begin to write all my this thing, this is partial positive, partial negative, partial positive, partial negative. I've written this one already. Now, these bonds are not polar. You cannot put a partial positive or negative on them. You cannot do that. So you look at this molecule, that water can form both hydrogen bonding and dipole-dipole interaction with this molecule. Actually, this molecule is what we call the methanol. And that is how you use only diagram to illustrate that in this. Now, we're getting close to the end of this lecture. It's been an important and an interesting ride. This one just very easy to do. You see, identify the most important. Now, when the word most important is used, I want to tell students this. What it means is that you should identify the strongest. So you can say the strongest interparticle force in each of. So I don't need, you just need the one that is the strongest. So if you study the molecule, know the one. Argon, remember the first problem did involve some of these noble gases. Single atoms are usually non-polar the way they exist, and therefore this is going to give you London dispersion force. If you look at this, this simply means HCl. Cl has higher electronegativity than hydrogen, so this is going to be a positive. It's going to be, no, this is going to be a negative. A negative is going to be a positive. Therefore, this is going to give you, it also has London dispersion, but because it has dipole-dipole, this is going to be a dipole-dipole interaction. In this one, this molecule now, of course, Between hydrogen and fluorine, this will be partial negative, this partial positive. Remember, this has both dipole-dipole, hydrogen bonding, and London dispersion. But because it has hydrogen bonding, that is what we're going to list. That becomes the strongest or the most important bond. Now, if you look at this, this is magnesium chloride. Magnesium chloride is an ionic compound. And if you look at this ionic compound, what simply happens here is that it's going to be surrounded by this ion, attracting this oppositely attract molecule. So this type of molecule we're going to be just ion interaction. Again, the last but not the least, which is also the same question, which says identify the most important types of intermolecular force present in each of the following molecules. If you look at this molecule, remember again, the best way when we looked about polarity of molecules, you need to first of all figure out what their molecular shape is before you begin to even figure out what their polarity is. If you look at this molecule is going to likely be what? A non-polar molecule, because if we draw the molecular structure, look at what it's going to look like. Now, if I can't see this, and then this is the one coming close to me, and this is the one I can see to the right plane. This molecule is symmetrical. When a particular atom is attached to 4 different things, the molecule is usually symmetrical. And most symmetrical molecules are what? Non-polar. Since it's non-polar molecule, the only type of bonding, interparticle force or intermolecular bonding that exists in non-polar molecule is what? London dispersion force. That is what we have here. We look at this again, carbon to oxygen. If you draw the Lewis structure of this, it's going to look this way. This is exactly what you're going to get. What it simply means is that carbon to oxygen bond is a polar bond. Remember, we did that in an example earlier, where we talked about the meta and all that. The carbon to oxygen side is polar. Because it's polar, this molecule will have both London dispersion and dipole-dipole. But dipole-dipole is stronger, so we're going to say this will be a dipole-dipole interaction. The last but not the least, again, if you look at this molecule, this is simply potassium and nitrate ion attracting themselves. So this type, the kind of this thing that will exist in this molecule of another one will be ion interaction, to be an ion interaction. It has been a wonderful ride in this lecture trying to apply the knowledge of our intermolecular forces. Thank you for listening and do have a wonderful day, and bye at this point.